I will focus on a new paradigm that we're seeing in computer science. It's called digital twins. And pretty much this paradigm, it brings together everything that we know in computer science: networking, databases, of course AI, edge computing, cybersecurity, cyber resilience, scheduling, cloud computing, edge computing. So the good news is that if you work in this area, the LLMs cannot write your programs. So LLMs doesn't understand the context that we need to write code for digital twins. So I think that's where maybe we need to train our MSc and PhD students if they have to be employable in the future. If we teach them simple database programming like SQL or TCP/IP programming, I think LLMs can do it and do it faster. So maybe it's time for us to look at our curriculum and see where we can train our taught and research students, because these are very, very complex systems of systems, which is beyond AI to encapsulate, capture, and then write automatic code. So there's a lot of need for human intelligence or human in the loop in programming systems. So in today's talk, I will highlight some of those issues which are both important from a research perspective as well as teaching and training perspective in terms of curriculum development. And I will go, of course the time is limited, try to cover as much detail as possible. It's not working. I think something happened when okay, so working now. Okay, so this will be my outline today. I will try to explain what do we understand by digital twinning. And of course, this is an emerging landscape. The definitions are not yet set. So maybe as researchers, this is our chance to set the definition and try to work in this area. Then after that, I will explain what are the application areas, and then we will look at what are the resource and data management challenges you need to figure out in context of digital twins, which are systems of systems. By the way, I generated this picture using Copilot. Again, AI comes into picture, and it took me like 2 minutes to draw 2 pictures. So AI is very scary. I just have to write a query that draw me a river with sensors and some visualization in the cloud, and it gave me this kind of picture. So AI could be really powerful if you use it the correct way, because if I want my content editor to do this picture, it may take a week but using AI, I can do it in 2 minutes, so it's quite powerful. But again, that's not the focus of this picture. The focus is to show you what do we mean by digital twin. So if you see in this picture, this is a city with rivers and all the sensors deployed across those. So that here is, how can we create the virtual replica of physical systems like rivers and cities and visualize it in a big cloud data center where you can make decisions, observe and monitor the physical systems using the virtual replica you create. So of course, one of the challenges is how do you create the virtual replica? So there's a lot of modeling required there, right? And once you create the virtual replica, the challenge is how do you mimic the real-time behavior of your physical systems, right? And that's where the IoT sensing or edge computing comes into picture. So inside the river, you see there are a lot of sensors that collect data over the river system and cities, and those data are transferred to the cloud-based virtual copy in real time, so that if that happens, your city planners can just sit in the cloud data center, control center, and see what is happening with your river, when the flood is going to happen, or what is the water quality, is it safe for people to go for all those things that they do, those religious activities. So having a digital twin is really convenient. You can have the sensors all across the river belt, and you can observe the whole behavior of the river without actually going to the river. But again, that is the conceptual thing, just instrumenting those many sensors on the river creating the virtual replica of the river system is challenging. And obviously that's where the research and training bit comes into picture. This will require you to combine things from networking, databases, cybersecurity, AI, and then you build this kind of complex system. So this is the reason why I call it systems of systems. If you look at on the right-hand side, that's a digital twin of a power grid. So digital twin for the power grid will be much different than, of course, for the what we have for the river systems and things like that, right? So the message here is digital twins are quite context specific, and they're specific to the physical system you are monitoring and making decisions about. So a digital twin for flooding is not same as digital twin for smart grids, or it's not same for digital twin for a building or things like that. So that means that AI cannot create digital twins on the fly because it's so much context specific. And the second question is the decisions that you make in a digital twin in a river setting is much different than in a smart grid. In river setting, you make a decision on when the flood is going to happen. In the smart grid, you make a decision based on how to do power demand supply pattern. So these decisions are quite different. Is it possible to adjust this a little bit better? This just keeps moving. Maybe use this mic, just remove this. Yeah. It's quite uncomfortable. Yeah. Right. So the digital twins are not a very, very new concept. I just saved this picture. NASA, the National Space Organization in America, they used to make digital twins of satellites since 1970s. So again, satellite is a one machine. You can make a digital twin of this quite easily because you know its mechanical parts. You can put a few sensors, you can do it, but conceptually digital twin has been around till 1970. But obviously if you want to make a digital twin for a river or a city, it's not the same. A city is a complex system of systems. You have buildings, roads, you have many rivers, you can have different air quality parameters, different factories, so this is much more complicated. Of course, how powerful is a digital twin depends on how do you model the virtual replica and how much sensing capability you can put in your city. So I work a lot with China. In Beijing city, they're creating a virtual replica of whole Beijing city. And what they're doing is district by district putting a lot of CCTV cameras, a lot of air quality sensors, a lot of smart transport infrastructure, and they are aggregating all those data sets into big data center. And they are doing this over like last 10 years. So the message I want to give here is, really build smart cities. You need to put money into these projects for not just 1 or 2 years, like 10 years, 20 years, 30 years. And I think as per my last meeting, they put almost 100 billion pounds in Beijing Smart City project. And now they can control the full traffic flow in the Beijing from the government headquarters. They don't need to do anything from each traffic lights, or they don't have any local control anymore. They can do global optimization. So these kind of concepts of digital twin is actually being adopted quite highly in China, Singapore. I'm sure in India there are also a lot of those projects as well, and Europe too. So this is becoming more and more reality. Like how do we combine this modeling plus IoT plus AI to create this digital twins of physical objects? So one of the underpinning technology for digital twins are, of course, simulation and modeling. But the point I would like to highlight here is digital twins are much more beyond simulators. So I think those people who know about flight simulators, the pilots are trained on simulators against different flying conditions, right? So they are again just a flight simulator, they are not flight digital twin. For it to become flight digital twin, that simulator needs to be underpinned by real-time data from flying conditions, from real flight path. So that's the difference between simulator and a digital twin. But having said that, simulation and modeling is one of the underpinning technology for digital twin, because when you create a model, it's always a simulated model of the rivers, of the virtual city. What makes digital twin is when you parameterize that simulation model with real-time IoT sensing data. And then you can see the real-time behavior. And once you have the data, you could do many what-if analysis. For example, if I have river in the Ganges river here, and you get data about the water level in the river, you can do what-if analysis on what if the rain intensity goes higher than what it is now, which banks will flood, for example, which ghats will flood. So this kind of what-if analysis could be easily done inside a digital twin. But again, that you can only do if you have real-time data collection capability from the physical object that you are monitoring. So simulation plus modeling plus IoT sensing and real-time data monitoring helps you make a small-scale digital twin. And again, of course, how much sensing you need depends on what sort of digital twin you are trying to build. So that's why I was saying a digital twin is much more than just simulation and modeling. So it includes simulation and modeling. So now coming back to the main point. So digital twin is a paradigm, is a way to construct complex systems of systems. So if you see this picture, you have this physical world that we all know about: smart homes, healthcare, smart cities, retail, connected cars, smart transport. And by no means this list is exhaustive. There are so many application areas. And right now in Europe and in America, in China, they are building digital twins for all those domains. The challenge here is, if I build a digital twin for say this building, this is not same as some other building. Okay, because the room configuration, the sensor, the lighting, the space, the air quality for this building is different than other buildings. So that's the reason why digital twinning is very, very much context specific, and each of them is quite intensive in terms of how much code you need to put in, how much IoT instrumentation you need to put in. So that's why I believe when talking to companies in Europe, there will be a lot of jobs in this area, because now everyone wants to automate how they manage their physical systems, like cities, buildings, hospitals. So like, in UK, National Health Service, we are building a digital twin of a human being, where we have put sensors in the human body. I mean, we all know that it's possible, right? And all those sensor data are transmitted to the general practitioner's computer. They build a digital twin of the patient, and based on that, they can decide how to change the medicine doses or when to call that patient for operation and things like that. So all these things can be done remotely without actually calling the patient to the hospital. So it's quite powerful in that way. You can remotely make decisions, remotely know about patient health, and remotely recommend medicines, and remotely organize operations. You can also send the ambulance to pick them if you think the condition is getting worse and worse. So this is why I say digital twin is so powerful. Everything can be done remotely through IoT sensing. No one has to actually be physically present at the object or near the human being to provide the care that they need, for example. So that was the example of digital twin for say healthcare, but similarly digital twin for industry 4.0. And the core idea is, by connecting machines in operation, you can use data, algorithms, models to make better decisions. The key ethos behind creating digital twin of anything is to make faster and real-time decisions in a more automated way using AI. Of course, any decision that you make will need to be verified by human beings, but through digital twin you can make those decisions as fast as possible. So if you look at, this is one of the Rolls-Royce jet engine that we see a lot in the Airbus or the Boeing aircraft. So we actually work a lot with Airbus. They say this engine has almost 100,000 sensors. And these sensors are sending almost gigabytes or terabytes of data to the co-pilot software of the Airbus or the Boeing. And then based on that data, the co-pilot software decides how to maneuver the plane, how much fuel to inject, and those kind of things. Again, the message I want to give here is the sensing and using the real-time capability has been used by industry for a long time. Like Airbus is using this kind of engine for the last 20-25 years. So they already have a digital twin of this engine. And at the same time, this engine sends data to the ground station where the Airbus engineers can actually see how these engines are performing and whether it is safe to fly now, also in the future. So using digital twinning, they can actually improve the safety of machines. And this is one of the classic examples. And because of this remote sensing and remote monitoring, that you can see this now very less and less accidents about the airline industry. Because now they can detect the defects in the different parts of this machine before it happens. So this is something called predictive maintenance. And of course, with the application of AI, they can actually know what should be the sound level of the fans, what should be how much fuel they should be consuming normally. And if you can train your AI with those input parameters, it can determine whether your engine is healthy or not healthy. So this is why this kind of technology are quite powerful in terms of predictive maintenance. Again, that's just an example of in case of planes. But again, I gave an example in case of virtual human being. So these applications are just unlimited, and obviously type of decisions and type of algorithms they will use to make those decisions will be different based on what kind of digital twin you are building. So obviously there are so many definitions available for digital twins from different companies. For example, one of the definitions that I like is from IBM that says that a digital twin is a virtual representation of a physical object, and in those virtual objects you inject the real-time data to understand real-time behavior and reason about real-time behavior of that object. Similarly, there's a definition from Siemens that says that digital twin is a virtual representation of a physical product used to understand and predict its physical behavior in real time. But across those definitions, there are two common things. One is you create a virtual model of a physical object and then you populate it with real-time data. And then inside that, you can use AI reasoning or other knowledge-based methods to make reason about, to understand better about your physical counterpart and then make your decisions. And again, what decisions that you make depends on what application area you're working on. It's not the same. So at the start of my presentation, I was talking about the satellite, and this is the model of International Space Station that NASA has currently deployed into space. So they have built the digital twin of this International Space Station, and based on this digital twin that runs on the ground, they can determine when the certain part of this ISS is going to fail, when it's going to need the maintenance, and they do so based on real-time data collection, the operational history, the maintenance history, and of course the space environment. So all this data is either available through sensing or historical databases, and based on this, they can actually manage, monitor, and schedule the repair for this satellite in an offline setting without actually sending anyone physically to the space to see what's happening with the satellite. So this is quite powerful. Of course, they communicate using space satellite communication protocols. So one of the, as you see in this picture, this is your physical world and this is the virtual world. And one of the key requirements of digital twin is that each digital object has a digital companion that can accurately model and predict its behavior. For example, if it's a road system with cars and buildings, you have to model all those things in your digital twin as well. And then you need to deploy your sensors on all those physical objects and populate it, and then you can make decisions using your digital twin. So we have actually built this digital twin in Newcastle city centre, working with the city council, and they use our digital twin to control the traffic flow. So they can visualize the traffic flow across different stretches of the city, and based on that, they can change the red and green signals so that the traffic flow is not only good to avoid the congestion, but also is better for the air quality and those kind of things. So this is the live project in Newcastle city centre that we are working from our department. And obviously, accurately modeling every physical object is not easy. It's difficult. It took us like 5 years to actually capture the city plan for the Newcastle city centre, the traffic lighting, and put fences all around those places, and then being able to make those decisions in real time. Yet, although we have all this data, we still have human in the loop sitting in the control center to actually verify all the decisions that we make are correct and safe. I think one thing I'll talk in the slide is like all this AI or digital twinning AI technology, they are very powerful, but the problem is to determine, are they safe to use? Can you rely on that, right? So right now we have very limited understanding of how do we verify the safety of these complex systems. So as I said, digital twin combine IoT sensing, simulation and modeling, cloud computing, edge computing AI. These all get combined together, you end up with digital twin. But then how do you verify if things go wrong? How do you verify if someone has hacked your sensor or hacked your computer, hacked your server? And if you have no mechanism to verify that, then all the decision this twin is going to make will be wrong. So that's where the research and training bit comes into picture. We need to train our students to, first of all, obviously program this kind of complex systems, but also they should have the theoretical underpinning to be able to verify its safety on an ongoing basis. So one of the things here is these are real-time systems. They are not offline systems. They are not like MySQL database sitting somewhere on the server. They are real-time systems interacting with real-time environment, right? So they need ongoing safety verification. So every data stream that you get from your sensor has the potential to make a digital twin unsafe, potentially. Again, based on what application area you're working with. That's why you need somehow automated, ongoing ongoing system verification technique, and that's where things like edge AI, edge artificial intelligence come into picture, where your AI can work on the sensor itself to verify that the data that you're getting is safe to be used to digital twin to make decisions. And obviously, to solve that problem in the UK, I'm running this 12 million pound hub on edge AI, cyber resilience that includes universities like Newcastle, Oxford, Southampton, Cambridge, Imperial, and we have this consortium of 12 universities, 20 postdocs, 60 investigators to look into this problem. How do we make AI safe for real-time systems? And of course, digital twin is inclusive of that. So it's a very challenging problem. We have just started working on that. We don't have all the answers, but at least we understand all the questions. And obviously, we will be able to find some solution in the next 5 to 10 years. So as I said, digital twin paradigm is quite new and exciting. And as you see in this picture, they have so many applications. Application in manufacturing, as I said, application in smart cities, application in healthcare, application in agriculture, in mining, the list is unlimited. I think these days you see a lot of companies, a lot of startups coming up with solutions in these domains, because if someone is successful in having a good prototype for this kind of areas, they have a big market to serve with maybe limited customization. Obviously, to develop digital twinning, you need a good team of software engineers, good team of researchers, good team of cybersecurity experts who can verify that things are going right, and digital twin is doing the function it is supposed to do. Right. So this is the minimum requirement for you if you want to lead a digital twin project or you want to write a digital twin proposal to DST to get some money. You need to understand these paradigms and then propose your research questions. You need to know how cloud computing, IoT, simulation and modeling, AI and sensors paradigms come together to create this digital twin technology in particular domain, and then you have to spell out the research questions. I will spell out some of those questions for you, but again, they are not applied to all digital twins, but some of them. Just to show that context again, so on the left-hand side, we will have the physical world. On the right-hand side, we will have a digital world where we will create your digital replica and connect your physical world to digital world. Very easy to say, but the amount of code and networking and cybersecurity challenges that we face here will be enormous. And each of them, like networking, cloud computing, AI, cybersecurity, they are their own research discipline as well. They are not just come together easily. So you need to have understanding of all those things. Obviously, I don't claim to be expert of all those areas. I'm running a hub with 60 other researchers from Imperial, Oxford, other places. So I'm expert in systems, but of course I work with people like Varun was here, right? So he's the AI team leader on my hub. So I don't claim to be expert in AI by any means. So of course we collect all this talent together and try to solve this problem. A little bit more context. So as I said, the underpinning technology for digital twin is IoT sensing. Right? You need to sense the environment. And so what we did since 2015, we set up something called Newcastle Urban Observatory. I am one of the research directors for this for computer science. So this urban observatory, we have deployed more than 3,500 sensors all across the Newcastle city center. And by doing that, we collect data about weather, traffic, water flow, water quality, and many other things, right? And we get almost 2,000 data points per minute in real time. So by doing this research, we actually learned a lot about how do we actually make digital twins of cities, digital twins of farms, digital twins of autonomous cars, those kind of things. So what I would say, like if you or someone else wants to work in this area, the first step to work in this area is to understand how IoT sensing works. And if possible, set up your own IoT sensing infrastructure. If not, if that's not possible because of financial reasons, you can work with us and we can show you, give you the free data that you can fit into your digital twin to write your papers, pretty much. Or maybe gain more understanding about this area so you can write proposals to DST. I mean, ultimately, I know even in India, getting money is one of the main things for all IITs and other stuff. So I think that's same as Europe and America and everywhere. As a professor, like my goal is to get 2 million every year for my research group. They don't care how many papers I write or how many citations I get or how many translation papers I wrote. That they consider as given. So it's about money, right? I'm sure in IIT also it's about money. Okay? And I think this area has a lot of money. I was successfully getting more than 20 million in this area in the last 3-4 years. This area has a lot of money. Obviously, if you pitch your research question in the right way, with the right industry partner and right team. I think one other thing I would like to highlight here is digital twins are quite complicated. If you see here, they are multi-tier systems. So obviously, this is not the TCP/IP model that we know about. Of course, the TCP/IP model is embedded inside this system, right? All the networking layer will have some kind of TCP/IP communication, right? But this is different than that. This is a T1, T3, T4 layer system that needs to combine your IoT sensing with your edge computing networks, which can be on different protocols, with your edge computing layer, your internet layer, with the cloud layer, and on top of that, you have your digital twin. So what is the problem with this architecture? There are two problems: the heterogeneity, diversity, and scale. And also the distribution, like the sensing layer lies in the physical system, like your rivers, your cities, your buildings. But your AI layer lies in the cloud data center, which could be in Amazon data center or Microsoft. So you have a system at the interface of both physical and digital paradigms, right? How do you trust this system? How do you program the system? How do you deploy the system? And if things go wrong, how do you redeploy your component? And most difficult question is, how do you debug the system? This debugging the system is not debugging your code in Java, Eclipse, or Python notebook. It's not. Maybe just one piece of code that you write for IoT sensing could be debugged in your Java Eclipse, but as a whole, in a holistic way, how do you debug if the data flow and control flow are correct? And possibly you will be looking at thousands of Docker containers with millions of lines of code working together to solve certain problems. And that's challenge, that's what makes it interesting, that's what it takes it away from the AI and LLMs to write code for this kind of system because it's very complicated and very context specific. But again, to write code for this kind of systems, you need to have understanding of a lot of things. Maybe you don't need to be expert in all those things, but you need to have basic understanding of how edge computing works, how IoT protocols work, how black box AI model works, what is edge AI, what is federated learning or distributed learning. You need to have a basic conceptual understanding of all those paradigms if this has to become possible. I wanted to give you another example of the flooding digital twin that we have built for Newcastle city centre. Similar to the river here, we have a river called Tyne River in Newcastle, and which is pretty much prone to flooding. So what we did there on the river, we have deployed water level sensors, CCTVs, and we collect data from them in real time in the monsoon or rainy season. And based on that, we feed that data into our digital twin, which is hosted in our private cloud, and we can predict the flood 1 hour in advance before it happens, using the traditional rainfall models and those models. Again, the point I want to show here is these models are not done by computer scientists. Again, we are not expert of that. These are done by civil engineers or water engineers. So these things are quite interdisciplinary. You have to work with people in School of Engineering, School of Geography, maybe Mechanical Engineering, and get their expertise. Most of their models will be based on complex physics simulations, which is not good for real-time data. So maybe you need to work with them, convert those models to AI models, surrogate models that can take the real-time data. So there's a lot of research to be done on surrogate modeling of the traditional models, because traditional rainfall models are just differential equations. They don't take real-time data from the sensors. So you need to work with them to convert those models into AI models. Again, some research is required on that, and each of the models are different for different cities. But again, this is a very good area to get money from the government, because this will not be done by the companies. It's too much context specific. They have to come here to solve the problem. I mean, one thing I would like to highlight here is, in terms of grants, you always choose a problem that is your local problem and is context specific, that Google and Microsoft can't solve sitting in Silicon Valley. And flooding is one of them, because they have to come here. So flooding in Varanasi is different than flooding in Patna, from where I come from, or Delhi or Bombay, right? So if you choose this kind of problem, the reviewers cannot say that Microsoft has solved this problem, or Google has solved this problem, or OpenAI has solved this problem. They can't, they have to come here. So that's one way to think about your research proposals if you want money in this area. Yeah, so that's what I was talking about. You know, our those rainfall models, those models are based on physics equations. Those equations, they cannot take the real-time parameterization well, so you need to work on AI models to train your surrogate models. And again, what sort of surrogate model you create is based on what kind of structure you are creating. You may need a surrogate model for the city air quality, or city flooding, or those kind of things. By the way, I got this slide from Varun, who's a senior lecturer in my group, who was a speaker before me. He's an AI expert. So we have also done some work on how to remotely monitor the stress on the bridge. So this was other work we did in Newcastle. So what we did, we have a bridge going across the Tyne River. We put sensors on different important critical points, and then we can monitor in real time when the traffic increases, how the pressure, or when the bridge is going to collapse. We can predict that in real time. So even for such small bridge, this digital twin is quite context specific, like in terms of which joints they have, what's the length of the bridge, and how many cars that can go in. Is quite context specific. Even to build this digital twin, it took us like 2 years to really go to the level where we can actually see these things happening in real time. So it requires a lot of work, a lot of research, and most of the solutions are quite context specific. There's no general solution. I can't take this code and deploy some other bridge, because those bridges structurally will be very, very different. And of course, we work with structural engineers and civil engineers to build the digital twin. Similarly, we are using flooding digital twin and some edge AI in the CCTV cameras to predict floods in real time, and we can make all the decisions using edge AI. So that was good motivation, good application. Now coming back to what are the open research questions that we need to work on, say for our research proposals, to run our research groups, or for our PhD students. So as you see in those digital twinning pictures, one of the challenges is data flow management. Like you're collecting all this data from different sensors, different physical objects. How do you collect and orchestrate the data flow? So for example, in our river digital twin or flooding digital twin in Newcastle, we have deployed 100,000 sensors across the river. But the challenge is, how do we collect those real-time data from those 100,000 sensors and feed into our digital twin? A massive challenge on that scale. It's not one sensor or two sensors or three sensors. So obviously we are able to do that manually right now through some scripting, through some procedures and stuff like that, because we know where sensors are, what IP addresses are, we can able to do that. But again, that solution is very much specific to our platform. What we really need is more automated data flow management tool that can automatically take the IP addresses of the sensors and start orchestrating the data flow to different AI models that need to make decisions. So the research is required on how to develop data flow management algorithm that can actually combine different kind of sensors, data flow together, and fuse those data and make it available to digital twin. This is an open question to solve. There are some tools that are like Kafka, Nifi, Argo that can solve your problem in some restricted way, but they are not automated. You have to write a lot of scripts to use them as in your data flow platform. So then again, you need to write your own algorithm that can bring together all this platform together to create your data flow orchestrator. Again, the challenge is the data flow orchestration is quite specific to your application. The data flow for, say, smart city traffic management is different than data flow for flooding or healthcare or those kind of things. So that's again, your digital twin becomes quite unsafe to use. You can't make decisions. For example, if my water level sensor in the river gives me wrong reading, then I can't predict the flooding correctly, right? Then how do I know the water level sensor is giving me correct answer or incorrect answer? Which is, the sensor is not here, it's in the river somewhere. That's a very hard question to solve. One way we do it, like when the rain is happening, we also send a drone there to see the water level. So we just don't rely on the sensor reading, but we rely on the drones as well to show us the image, and we can use certain image processing to verify that sensor reading as well. Again, this solution is specific to flooding. This doesn't apply to other applications. So you have to find different way to monitor data quality, a certain data quality, and then based on that, determine the safety of the system. Again, a very, very difficult and unsolved problem. And I was saying, the data or the system can become unsafe because of battery failure to sensors. For example, your water level sensor can just flow with your water. It's just gone. It's not there anymore. The hardware can fail, the software can fail. When you update your software, there could be bugs that you introduce in your sensors, so everything can just create problems for you. So because these are systems, there is a likelihood of a lot of problems being created at the same time. And then the issue is, how do we detect, monitor, and fix those problems? And currently, both in open source as well as research communities, such solution doesn't exist for such complex systems. So as I was saying, if we have these sensors deployed in the rivers and cities, the cyber attack can happen, which is quite common these days. The faults and failure can happen. And if things go wrong in your sensing layer, everything that you do in your digital twin becomes wrong. So this doesn't work. So that brings us to two kind of problems. One is seen and other is unseen. So it means literally what it means in the English. Right? Seen means it's those problems that we are aware about that can happen to your digital twin across those 5 layers. We don't know how to solve the scene problem as well right now. There's so many scene uncertainties like battery failure, weather conditions, network congestion. We don't know how to solve it. But other issues, unseen things. Because these are so complex systems, a lot of things interact with each other and a lot of unseen activity happens. That also makes your system unsafe. So we need a lot of research, and also we need to train our students to understand what are the seen and unseen uncertainty boundaries and what kind of AI algorithms they need to detect, monitor, and field these kind of seen and unseen uncertainties, both in terms of cyber attacks, faults, and failures. Just to solve this problem, we got this 12 million pound from UK government because this applies across so many disciplines: smart manufacturing, airlines, flooding, all those things. Because this is very, very important. If IoT or a real-time system management is going to be possible, we need to solve this problem first. If we don't solve this problem, then all those technologies are of no use, for example. So say you put a digital twin together, then the question is, how do you monitor and debug the problems real time? How do you monitor what is happening in your different parts of the systems, whether they are functioning correctly, whether they are doing what they are supposed to do? It's an unsolved problem. How can you distinguish between faults, failures, and cyber attacks? Some faults, failures just happen on their own, but some can be introduced by cyber attacks. How do you distinguish between those? And the landscape for this is unlimited. You cannot go to LLM and ask, what are the faults possible with my federal digital twin? They will not give you any answer because no one has trained the LLM with that answer. Because no one knows it's a research issue. So of course we need to do some threat modeling, fault modeling, failure modeling, and then write papers on those, and then we would be able to answer those questions. And so once you realize that something has gone wrong, then the next issue is, can we heal those things? Can we fix the problem? Again, healing is quite context specific. Not all problems could be healed, like your sensor just drained away with the water. That problem can't be healed. The only healing for that is to physically put your sensor, for example. So these are some of the questions that are relevant to healing, like how to holistically heal across the 3 years. It depends where the problem happened. If the problem happened in the cloud, maybe it's easy to heal. You can just start a new virtual machine because there's a server problem, right? But if your problem happens on the IoT layer where the sensor has a malfunction, that's not so easy to heal. So again, the message here is the healing in context of systems. Systems like digital twin is quite context specific, and every problem requires a different healing action. It's just like, it's not like if you want to avoid data loss in the cloud, you just replicate. Replication of devices and data is not possible in IoT or digital twin because it's real time.